So this is a matrix that we are going to study. This is rectangular MN matrix with IID entries with zero expectation, unit variance, and the force moment finite. Rm is not random, and we only know that it has eigenvalues tau alpha, and the corresponding counting measure normalized converges as m tend to infinity to a certain limit. In our goal to study the eigenvalue distribution of this matrix, this random matrix. This is a random function, and our goal is to prove two facts. They are interrelated, by the way, that there exists a non-random limit with probability 1 of this measure, and we would like not only to prove the existence, but to find roughly, okay, in certain sense, explicit form of that measure. And so let's, oh, yeah, excuse me, where is the theorem? And the theorem, corresponding theorem is like that. If we have a matrix explained above, and we assume that the force moment infinite, and this characterization diagonal matrix Rm, Hermitian, M by M, and provided that these conditions are the case, we would like to prove that the counting measure of the matrix converges to non-random limit, and this limit, if we write its Stichius transform, which was explained last time, then the Stichius transform of the limit solve uniquely this equation, and at the end of this part, I'll show you how this equation could be solved in certain simplest possible case. Yes, and we are looking for the solution. I said it in such that this limit is 1. Well, and the first step, okay, we discussed already that it is not the most general form. There is a more general form where we do not, these conditions are omitted, and the result now, and the matrix Rm not necessarily positive definite, but nevertheless its normalized counting measure exists, limit exists, and then we have similar equation, but now in the whole complex plane except the cut of the positive semi-axis, and this solution, this is Stichius transform the limiting measure, and this of this cut under this condition, yeah, that one in this one. Yes, well, in the first step of the of the of this goal is an important additional fact, auxiliary fact, according to which if we have our measure, which we are looking for, it is our our subject to study, then the fluctuation of this measure, fluctuations by definition, this is random variable minus its expectation. Fluctuations tends to 0 as the size of matrix. The form of this matrix written as well as here in a bit different form, which is quite convenient and in fact informative. We introduce we denote the rows of x as x alpha. Now we renormalize them. So this vectors is y alpha, capital L alpha, and it's easy to see that they satisfy this condition that the mixed second moment is diagonal if you want with respect to the second index. And now it's easy to see just writing this matrix product, which is right hand side. It is easy to by this formula, or this is matrix formula, but we recognize that if you have a vector and you have a this product of two components. This is in fact the matrix entries of the rank 1 matrix determined by Y. Well, and the more, what is going on? More just for just that this form written not in the entries but just in matrices themselves is written here, and you see that we can always write this expression which is in the top line. We could just okay, single out just one term, arbitrary term, a fixed one, just choose alpha and write this matrix in that form. And it is evident that in this case, the matrix which is here, M alpha n, it doesn't depend, I just stress, it does depend on Y alpha. And it will be quite important property which will be used many times below. Well, uh, this is first thing, so we write the matrix in that form. Now we recall the intermittency property of eigenvalues of any Hermitian matrix, which is just perturbed by rank 1 matrix with positive coefficient. You have this bound which is valid for any realizations for random variables. Yeah. So if the number of eigenvalues divided by n in any interval minus number of eigenvalues of that matrix, they differ at most 1 over n. Yes. And now by using this property, we recall this martingale type bound of fourth order, according to which if you have a certain statistic, which was explained last time, so you have a function phi capital, which depends on m variable, you insert instead of variables certain random variables, psi alpha, independent, identically distributed, and you write again the fluctuation of this statistic. Okay, this is fluctuations. You would like to compute or bound the force moment, and this force moment is bounded by this sum where delta alpha were also explained last time, and I'll explain on next slide. Ah, yeah. So this is explanation. So we take this general bounds that I mentioned that was explained already 2 times. Yes, we take particular case, we view our counting measure as a function, in fact, the rows of our matrix M. Yes, and we use this bound where delta, what is delta? You take your random variable, which is a function of M other random variables independent. You make the expectation, integrate with respect to the probability law, uh, alpha minus 1 times and alpha times, and this difference is in fact delta, which we have here. Yes. Well, and since this psi alpha, they are independent, I stress once more, yes, we can, yeah, the expectation E alpha and the expectation with the rest, and to rewrite the first line in that form, yes? And then you do quite serious things. You just recall that the matrix M alpha doesn't depend on Y alpha, with respect to which we have this expectation. Therefore, we can write this sum in this form. Yes, so we can subtract and add to new M itself the new of this the measure of this matrix, and you can, which is most important, you can introduce this random variable which for every term of this sum, which is under sign of E, the previous bound, yes, and because of that, the right-hand side of this delta is bounded by what? By 2 over n. Well, it is not random variable, therefore we can forget about the the expectation 1 alpha minus 1, and we arrive to we put this bound to the bound written on the previous slide, excuse me, here. We have n in front, there is sum which gives also n, and we arrive to this bound. Therefore, we see that the fluctuation they decay with respect to the order of matrices 1 over n squared. Now, you insert this thing in the Borel-Conté dilemma. I believe that it was discussed on the exercises. Okay. And then we arrive to the statement that the, the the, this random variable, which in the language probability theory is called centered random variable. We have random variable nu, and we subtract its expectation, and we say that it's centered random variable or fluctuations. There are different names, and then we see that fluctuations decay quite fast to provide us with convergence with probability 1. Yes? Well, it's very good. And in a,
And Andrei,
let's let's
interrupt.
continue.
Sorry for interrupt
Sorry?
you. Sorry for interrupt you. Yesterday we discussed this lemma, but it's there was many questions. That's why it was very useful to repeat it. But it seems to me that we are on page 27, something like this now. So we discussed and we proved
But we
what.
are on the page 21, Anya.
Yes, but
Yeah,
but
what is the question?
yes, yesterday we was on page 27. We finished on page 27.
Yeah, okay, let's go.
Okay, but this was students have many participants, many questions, so it was very useful to repeat.
Okay, but please, I am ready to questions.
Okay, now we do not have questions, so because it was repeated. So
Well,
we
yes.
prove this what we need up to conditions 1, 3, as far as I understand.
Yeah.
Yeah.
So please.
No. So thank you. Now questions.
Do you have any questions on the second part of yesterday's talk? If no, then we can just resume from the slide 27, I guess.
No, I'm just repeating.
No
You would like
more
me to
questions.
go?
Okay, no more questions. So we'd like to resume from 27 when we stop now. So.
Okay, let me just summarize. So by
Okay.
doing nothing as linear algebra, we are able to arrive to this relation. And now look at these relations, 24. If we are so smart that we could be able to make this replacement, to replace H alpha by Fn, then instead of this relation, it's just identity. We obtain already asymptotic relation because we assume that I can replace modulo certain error, which at the moment I do not know, and I do not know whether it is valid, but nevertheless, let's assume that it is possible. Then we arrive to that equation. And so now what do? We use the fact, so it is rewritten in that form. Then we use the fact that the Fn minus t is in fact just a restriction of analytic function Fn on z. And if you have a family of analytic functions which are uniformly bounded, then there is a subsequence. It's called Montel's theorem, subsequence of these functions that converges in a certain compact set of the complex plane. We choose at that complex set just an interval on negative axis, which is here it is written, yes, and we have this relation then, and we are able to pass, if it is correct, if we do this, we refer to this theorem. By the way, it is not necessarily, you can use the fact that the measures themselves, they are also possess this property that you can choose the convergent subsequence. In any case, whatever you do, you can replace here Fn by F itself, again, modulo certain different from that error term. Okay, it's simple algebra, yes? And then we recall the definition of the counting measure of tau's. It was denoted new rm, yes? And we can rewrite this relation, this sum, as an integral with respect to this, as they say in probability theory, empirical measure new rm. Yes, and then we can pass to the limit because by the condition of theorem, this measure weakly converges to a certain measure nu r, and we arrive to, we can replace these things by more, I don't know, by limiting form. Okay, modulo, of course, again, certain error, but if we believe that everything else, as I said just now, is valid, we arrive to this equation for a function f. And now, to be on safe side, okay, this is a claim, in fact, and now we have to justify this claim. Yes, and this is 27. Yes, what is? Yeah, before justifying the claim, this is, as far as I remember, we just finished on these things. Before to justify this claim, okay, what do we do? We just mentioned that, okay, let's proves that if you have a random matrix, we have counting measure, then there is a subsequence of measures that converges weakly to a certain limit. There is a corresponding subsequence of TTS transforms that also converges to a certain limit, and this limit satisfies this equation. But since we were dealing with subsequence, there could be many subsequences with many limits. And what is the issue? How to solve this? How to answer on this doubt? We have to prove that limiting equation is uniquely solvable. Yes, solvable. And it is what we claim. So it is just to remind you that we have this. Yes, we would like to prove that it is uniquely solvable in the class of positive function. And here is a proof. Assume that there are two sublimits. Is they are different? Therefore, there are some points, some values of the argument of these two functions where the function do not coincide. Yes, it is written here. Excuse me, I forgot to here. There are minus here and here. Yes, and then what do? We just write the equation, this equation written on the previous slide, this equation for f1, f2, we subtract, if we obtain the equation, yes, sorry. No, should be. Here. The equation written here, but not precisely that equation. But when you just subtract and write the result, there will be here f1 minus f2 from the left. This will be left-hand side. There will be this factor to the right-hand side. But since we are dealing with the values of t where functions are different, f1 minus f2 is not zero, so we can get rid of, and we obtain this relation, yes? But now we recall that, okay, tau are positives, and f1 and f2 are also positive because of this formula. And because of that, we can replace tau square times f1, f2. Yes, we just get rid of 1, yeah? And we get, so what do? We have tau square f1, f2 in the denominator, in the same things here, f1, f2 new square, so it is strictly less than 1. And this is contradiction that proves that indeed the equation of the previous slide is uniquely solvable. Yeah, this is in fact this is a theorem. of course, so we prove the theorem modulo proposition from myself. Let's replace. Let's do this replacement. Yes, let's replace in our identity matrix identity the expectation of quite complicated object just by replacing f h and h by f. So we have to prove these three facts that provide us, we start to see. I start from the first fact, I have h and alpha, and the last I have fn, but I go through three, so okay, there are three things to prove. Let's look to the proof just quite shortly because there is. Here we start the first assertion. We have to take h alpha minus t, which by definition just the quadratic form where the matrix is the resolvent of the matrix M and alpha, which by the way does depend on y alpha. So y alpha is here, but in G alpha n there is no y alpha. Thus, just recall my tutorial in which I showed you that if you have a quadratic form where there is certain matrix, quadratic form formed by a matrix by a random vector, but a matrix could be either non-random or random, but dependent on y. Of G, I repeat, this is because G and alpha does contain y alpha and expectation with respect to alpha only. And the variance, it is bounded by uh, something divided by what is important. This variance has this order of magnitude. Therefore, variance also vanishes. Yes. And now what we have to do. We would like now, seeing that they are quite almost identical, H and alpha and G and alpha. What do? We just take equation, and what I do in the right hand side, I just write Fn right here, Hn minus Gn, and do the difference. And what do I get? Just let's see. Well, so I have this property. I can replace again any denominator just by one, and then this complicated expression will be, and I use, of course, the property that we already used, that the expectation with respect to every y alpha, they are independent, they are factorized. And then what we have do, we can write, let me show. So let's do this. We write in that form, then we get rid of denominator, just replacing the denominator by one, each one, there are two, and we are left with this expression. Now we use it is written on previous slide. You see there is Cauchy inequality. If you have the expectation of a certain random variable, non-negative or absolute value, then by Cauchy inequality, this is bounded from below by variance, square root of variance. Yes? We apply this Cauchy inequality. So we have this expectation, particularly with respect to E alpha. We apply the Cauchy inequality to get that one. We know that the variance is of the order 1 over n. And then eventually we see that indeed this error term, which comes from the replacement h and alpha by g and alpha, it vanishes and tends to infinity. Yes. So we justified the first replacement. Now this second one, we would like to pass from g and alpha, which is a trace of this matrix G and the resolvent of our matrix, you remember M and alpha, in which we subtracted y alpha. So we would like to replace this resolvent by the full resolvent, yeah? So we would like to show that the difference of this function and that function, the expectation again vanishes, yes? What do? We just write, we just use the definition of each of these functions. We have this thing, and now what we have here, these are resolvent of two matrices. They differ by the rank one. So we use again trace okay, uh, rank one perturbation formula. If we have this bound, it was discussed on the first lecture. This, if your two matrices they differ by rank one, then this expression which contains this resolvent is of the order 1 over n. It is written here. I remind you what is A. We work in the interval of negative semi-axis between on interval A B from A to B. So I replace the argument t, which varies from minus b to minus a, just by the point which is closest to the origin. It is upper bound. So and we get the bound. So we justified the second thing, the second replacement. Now we are coming Gn by its expectation, which is our Fn. So what do? We do again, first, we use their definition to obtain this line, yes. Then we use again Cauchy inequality to pass from the expectation of absolute value to the variance, and we arrive to that things. And now we use again martingale bounds, but now the second order, the simplest one. Let me remind you that in our tutorials, we considered two martingale bounds of second order and the fourth order. We have used already fourth order in our proposition. Now we need just take, but now we take as a phi, not the counting measure as in proposition, but just this. Okay, is in fact this is its Fourier CTS transform. So I write again the fluctuation of these things are bounded by the sum of delta alpha, which are written here. It is just taken from the general martingale bound. And now what is it? Again, we do the same. We single out, we write explicitly what is it. These are just expectations with respect to just a part of variables. And we proof of proposition. What we have here, we have 1 over n trace g minus some expectation of that trace, yes? And again, what do? We do the same trick. So we just take g and replace g by g minus gn. Again, I don't know, there is certain, okay, parenthesis, okay. It is a misprint, yes? So we have this thing, and again, I use the fact that the matrix M and alpha doesn't depend on Y, therefore it's resolvent the same, and then we can replace this expression by we use the rank one formula according to which this thing is bounded 1 over n. Yes, and we arrive to this bound. Okay, then our delta of alpha is just a square that is bounded like that, but there is a sum in the martingale bound which, which cancel one power, but nevertheless, the total, the final error term which comes from this replacement, the third one, it is 1 over n. So we justified our bold assumptions that we can replace h and alpha by fn, and therefore the theorem is, because I am going now to consider an example, so as for the proof, it is finished. No? Well,
Any questions?
Anya, I'm in your
Okay. Any
order.
questions?
Could I continue?
Yeah.
Well, okay. Now let's consider an example. Let's take the let's take the matrix R, which was central here. Let's take that it's just one, simplest possible. And this is a simplest possible matrix of this class. Yes. And then we need to know in this case if we take R is just the delta measure. It is concentrated at the point one. Yes. Yeah. And then you insert. Let me show the equation. Okay, you have this integral, but now your measure is just delta function at one. So instead of integral, you have the just integrand in which tau put set to one. And you'll find that this equation, this is just, we are lucky because now we see that f, we are looking for f satisfy the quadratic equation. Well, we can solve the equation, but there are two solutions at any quadratic equation. And here we have to recall that it is not any positive. Because of that, I have to choose here plus. You remember that when you solve the quadratic equation, the coefficient in front of first power, there is always the square root plus minus here. There should be square root plus minus, but we have chosen one because of this condition. Now we have this expression, but it is valid on the negative semi-axis, yes? But you can easily check, it's just an exercise, simple exercise in complex variables, that this function, there is a square root, and the square root is a not completely simple thing in complex analysis, which, if we write this expression just boldly, so we can check that if z equal minus t, you get to this equation, but to have this correspondence, you have to choose the branch of root which has this asymptotic behavior for large z, not necessarily, now it could be any complex, and you can easily check that this branch is the following. It has the cut between the 2 points a plus minus 1, and on the upper edge of the cut, this branch is positive. Now we have to recall the CTS-Perron inversing formula that allow us to pass from the CTS transform to the measure. What is the CTS formula? CTS transform formula, you can look in your slides, but it's easy to explain. To get the measure, you have to make the limit. Here z is complex outside of positive axis. But now I would like to go to the positive semi-axis from above, because if I will go from above, my branch will be positive, and by the TTS-Perron formula, the measure is just imaginary part of its TTS transform taken on the real axis from above divided by pi. And we arrive to the formula for our measure. It's, by the way, a very nice exercise to find this limit. Yes, so our measure is as follows. So there is still a certain atom at zero, there is delta function with a coefficient 1 minus c, but you see, I introduced just positive part. You see, x plus is defined as a positive part of x. Therefore, if c is less than 1, there is always absolutely continuous part which has a density, and the density is written here. So you see that there are cases, unfortunately, they are not so numerous, when you can explicitly solve this equation and you find a measure. But it is rather an exception than a rule. And in most cases, you have to deal with the equation for the CTS transform, trying to subtract information from the on the measure, dealing with its CTS transform. Yes, and just for fun, I'll show you two cases. This is just the histogram, not so numerous. As far as I remember, something 50 samples, and you see that with a c less than 1, we have a delta function, which is described by this peak consisting just of the line. You have absolutely continuous part, which is not smooth because okay, you use not a computer, but just some calculator maybe. Not so exact, not so I know extensive uh, calculations. And on the next slide, you'll see the picture of the graph of this measure when c is bigger than 1. Also, this is more exact, but not so exact. So the continuous line, this is theory. This is a formula that you have just seen. And here, just again, numerics. And you see that delta function disappeared. You have just continuous part, which is of that form. Okay. So I finished the things, now the questions, because if not, I have still, oh my God, I have just 13 minutes, not too much. I would like to know the materials that I would like to present. It requires more time, unfortunately. I would like to show you some intriguing application for black holes, but well, so it is I believe that it is not so. Okay, active field in which they are studying entanglement entropy. I'll explain by now in a certain object which is called black holes. I will not explain what are black holes. It is something quite interesting. First discovered by Lagrange in classical mechanics, and then it was found that okay, there was English physicist Hawking who made this field very important. Well, and there is another field called quantum information theory, which was, oh my God, since now it's good. Just Well, let's start. We are dealing first. Let me give you several facts from quantum mechanics. In quantum mechanics, the state in classical mechanics, the state is just a point of phase space or UV distribution. In quantum mechanics, you describe your system by giving its whatever it means, so-called density matrix, which is just positive definite operator of trace 1, acting in a certain Gilbert space, which is called state space. And so in general, it is just but there is a particular case when your matrix, positive definite matrix, just okay, these are so-called Dirac, I had no time, Dirac notation. It is just rank one projection. So you have a vector psi, and we know already what is a projection. So it's rank 1 projection, and it is called pure state, while the general case called mixed states. Now there are cases when you would like to your big system consisted of two subsystems, two parties, yes, and then okay, I believe that the people in audience know what is the tensor product of two Hilbert spaces. So it just okay. If you have in classical mechanics two particles, you need a function, two variables to describe them. In quantum mechanics, we say that we need the tensor product. And you have a function, you have a system that lives in this big system consisting of two subsystems, and you say that your state is entanglement if you can't write it in that form. What does it mean? You have a system which is described by a function of two variables, and you say that it is function system is entanglement if you can't write its state as a product of function of one variables. So it is in probability, it means that you have a random variable that is described by its its probability law is a function of two variables. This is all. Well, and there is very simple example. Assume that your spaces are both just two-dimensional. Simplest quantum mechanics is in two-dimensional Hilbert space. You have a basis which is described in this form, and if you write the vector of your tensor product of that form, it's a special name, Bell State's Nobel Prize, by the way. So it is this state is not entanglement because it's sum of two not entanglement states, but sum is not a product. So it is simple but quite informative example. And now there is a question: how to find certain numeric characteristics of the fact that your function is not function of two variables, but is a product. Excuse me, not it is not product. Yes, and physicists found quite interesting functional of your state row. It's called von Neumann entropy. It is just I remind you that rho it is positive definite operator is rank of trace 1, you can write a function of this operator and you make a trace. You can easily check that if your state is just rank 1, if you ask the question, by the way, completely mathematical question, what is the maximum, possible maximum of this functional of a positive definite matrix of rank 1? It turns out that the maximum is 1 over n. Yes, and it is achieved on the matrix which is just 1 divided by n. But matrix 1 contains all the vectors with the same weight. Yes, therefore, we see that entropy is maximum. Therefore, the entropy is a not bad functional, numerical functional, which varies from 0 to that characteristic of the entanglement. Let me give the very simple. You have a physical phenomenon, electric current. We have three characteristics of the current: volts, amperes, and ohms. In fact, there is much more. So here is the same story. You have certain physics, certain object which is called, okay, density matrix, and you would like to check whether this matrix is a product of tensor product of two matrices, or in probability, you have two random variables, you have joint distribution, you would like to know where this distribution is a product of distribution, therefore, when these random variables are independent. Yes, so we arrive to a certain guess, which is just can be justified only by experiment, by physics, that entropy is a good measure. There is a jargon quantifier of the entanglement. Yes, and now uh, a bit more. So it turns out that better to consider not the complete density matrix, but just it's called reduced density matrix. It's like again probability. If you have a probability, okay, two dependent random variables, you are interested only in one of variables. What do? You just integrate out the second one. But in quantum mechanics, instead of integral, you take a trace. So this is analog. So you have two random variables, quantum random variables with joint distribution. You are interested in that one in A. So you just pass to reduced density matrix rho A. Yes, and so it is analog, I said, quantum mechanical analog of marginals in probability. And you determine, you define, you set, now you calculate the entropy, not the whole, but just this part. Bell state, which I wrote before, just the sum of two, yes? And the entropy is zero. Because, why? Because we have seen that this is just pure state, just a vector on Hilbert space. And in that case, the entropy is zero because, you see, because, why it is zero? Because if you have a just rank one, we have a quantum mechanic, we have a quantum system consisting of two parts. Because of that, it calls bipartite. And we would like to check whether the system is entanglement or not. What does it mean? It means that its density matrix, which is a main, which is its characteristics from which you start, it describes the system, whether it's a product, tensor product or not, the density matrix of two subsystems. So what do? We take our matrix for whole system, we take so-called partial trace, which is an analog of integration with respect to one of the variables. In quantum mechanics by two famous people, Dirac and Landau, in the 30s. And then we would like to calculate this quantity called entanglement entropy. And we believe that if it is a kind of measure, numerical measure of the amount of entanglement, that what does it mean? Okay, we would like to measure the amount of entanglement by using this characteristic, this cousin of amperes. Yes, well, uh, uh, and now this is a general introduction to the quantum mechanics, more precisely quantum information theory. And now I am going to discuss quite shortly a very interesting quantum system, which is a black hole, quantum, because, as I said, black hole were invented long ago, quantum mechanics in the 18th century by Lagrange. Not invented, but just he found that if you have a Newton gravitation and you have a system in which gravitation very strong, then there is certain, crisis. There is the systems, comes to, tries to come to the in the 70s of 20th century just said that we have to quantize quantum holes, black holes. And quantization, what does it mean? That black hole is not completely black, because according to classical physics, anything that fall the black hole never coming back. So because the strong gravitation, it attracts quite strongly anything that near the hole. But then Hawking told that it is in classical physics. If we are in quantum physics, then the black hole could emit photons. Okay, there is radiation or black hole radiation, and there was a physicist in 93, the name Don Page, that said, let's try to compute the quantumness, the entanglement amount of entanglement of black hole when it is quantum, that when it evaporates. And he said, okay, I would like to be very simple. What do? I described this is quantum hole, but, excuse me, black hole, but it is viewed as consisting of two parts, black hole itself and its radiation. So it is a kind of K and R, discrete variables, yes? As I said, tensor product is just the function of two discrete variables. By the way, function of two continuous variables is also tensor product, but two functional spaces. Yes, yeah. Index K describe the whole. Index L describe the radiation. Yes, and he said, I know nothing about black hole. Okay, it's completely important, unknown thing. Therefore, I assume that the vector, which the wave function, maybe you have heard this name, quantum wave function of black hole, it is just vector which is uniformly distributed over a unit sphere in the corresponding space of dimension capital L, capital K. So it is, he called it, it is called, it is a principle complete ignorance. So we know nothing. Therefore, all the vectors, all the vector of unit length, they had to be normalized. Wave function has to be normalized. All of them are possible with equal probability. So complete. Now I would say that it is not a black hole, but black box. So we know nothing. Yes. Okay. So now, if yes, we have a now, if you have a rank one operator, it was already in our tutorial. So what is the corresponding uh, okay, the corresponding projection? It is just the product of its components. Yes, we have vector, we write components, but every component is indexed by two indices. This is a Hall, this is a radiation. Yeah, this is density matrix of our system. Now we have to pass to reduced density matrix. We have to sum over the degrees of freedom of the whole of case. So we do this summation, and we arrive to the matrix of that form. The indices are L1, L2. They describe our radiation. If we would like to know what is the amount of entanglement, yes, of this system. So we have to compute the von Neumann entropy, which is denoted by SLN, of this random matrix, by the way. So we are now in the mixture of quantum gravitation and random matrix theory. This is a bit unusual random matrix. If you have a vector which is distributed over unit sphere, completely hard distributed, I would say. So this matrix is random. Considers, except that now the trace of this matrix is 1. And it is called in random matrix theory restricted trace ensembles. Nevertheless, it's completely well defined. And the question about, and to compute uh, uh, the entanglement entropy, what we have to do, let me remind you what is the entanglement entropy. No. This is a trace of this matrix, yes? But we know how to assume that we know the eigenvalues for alpha, yes? Assume we know its eigenvalue. Then we remember that the trace, when you did, remember, when you did the trace of resolvent, what did you do? You just sum, okay, there is a definition of the trace. It is sum of diagonal entries, and by using spectral theorem, you can just sum eigenvalues. So you can introduce the normalized counting measure of rho alpha, and then to make a trace, lambda, log lambda, nu de lambda, like before. Well, so we reduced our problem to the random matrix problem. Yes, from quantum gravitation to random matrix theory. The Don Page, which proposed this approach, he was not so knowledge on he was not knowledgeable on random matrix theory. He made calculations, many calculations, and just proposed the formula. This is a page on 93. Just empirically, just looking at the result of calculation, doing the graphs, etc. He found that if you take this matrix and compute the entanglement entropy, it will be asymptotically again massive enough. So both parameters are large, but ratio asymptotically proportional, like it was before. Then he got a formula, by the way, not analytic. You see the formula when this ratio, when radiation is not so strong, I remind you, L, it is somehow the size of radiation. You have that one, and if radiation is strong enough, you have the different formula. Plus something which is, okay, smaller order that written here. Well, this is the page formula. It was recently, afterward, it was calculated by several people more knowledgeable about the random matrix theory, but all of them, they used this matrix, which is not so usual, and a bit corresponding calculations, they are a bit special and a bit involved. Because of these restrictions, the trace of matrix is one. I propose, just as a toy model, let's consider a bit different construction of that row. Yes, let's consider our families that we already considered. We have random variable, independent, normalized like before. And now I take again, like before, the rectangular left upper corner of this infinite table. This will be a matrix, yes. And I would like, I would like to compute the trace of its square, yes. So I compute this trace and I found that it's written here, yes. Now let me take now I view this thing not as a matrix, but as a vector in the space, in the tensor product, because there are two indices, yes. So I take this one and I form the matrix written here. I take my matrix, I divide by the trace square, square root, and what do I obtain? I obtain the unit vector. This is again on a unit sphere, but in general, this vector is not uniformly distributed, is not hard distributed. It will be hard distributed only in the case where all x's are Gaussian random variables. So this is a page case. Otherwise, they will be different. So in a way, what we are proposing a bit different principle of complete ignorance. We do nothing about our object if it could be described by independent random variable normalized by hands in this way. So let's consider this matrix instead of page matrix. What do we have? Let's see. So I write, this will be now it's my density matrix over the whole system, yes? Now I can just, it is the object from which I started. I divide the both denominator in numerator by the same, by k. K is the size of black hole, yes? And what do we obtain? We obtain our old friend. We obtain the sample covariant matrix. It was, by the way, analyzed in the exam entropy. Look, we have our row. Now we would like to compute its, take row, log row, you compute the trace. It is simple calculation. You see that it will be just simple algebra. It will be written in that form. There is a first term on the right hand side and the second term, yes? First term is just a random variable, certain. Here it's also random variable, and here the trace of the matrix. And if we introduce its eigenvalue counting measure, then we have to divide this by L and multiply the factor, and I arrive in that formula. Now, what is the first term? By definition, it is just the product. Now, recall that in our tutorial, I mentioned the strong law of large numbers. What does it mean? You have a certain sum of independent random variable. So divide this sum. If you divide this sum by their number, a number is KL, then it tends with probability 1 to the expectation, which is in our case just 1. So we see that if I take y, which is z divided by k, then our y is just L, yes, with probability close to 1. And this log is just log L, yes? So we already understood what is the first term on the right-hand side, just log L. Now let's pass to another term. We know that if you divide y, so if you write these things again by the law of large numbers, oh, I don't know what is going. No, it's finished, excuse me. So let me see. So we have these things, I would like to finish here. So we arrived to the, so these things, here is log, it is, this factor is 1, in fact. It follows from that formula that asymptotically this factor is 1. And here is just, you have to compute the integral. You remember these distributions that I mentioned. You have to compute this integral, it's just standard calculation. And you find that second term asymptotically exactly the same term that was in the page case. So we just, by using standard trick, nothing special like previous authors, you can prove that it by changing a bit the notion, a bit general, now you say that you are completely ignorant, not when you're the vector that describes you is uniformly distributed of the multidimensional sphere, but just because we have independent random variables and we write our vector in that form. Then it is more general case. The page case will be if x is Gaussian, and we have in the page computed on the expectation of the entanglement entropy. And we, with our elementary knowledge from be the same. First, for more wide class of states of quantum system, and not only expectation, but the whole things with probability 1 behaves in that way asymptotically. So we have somehow, this is a nice toy result that saying that random matrix theory could sometimes serve to other fields. There are many applications, and this is just maybe not most important. There are, for example, application quite serious to mathematical financial theory, to physics, etc. But they require a lot of time to explain. But this is simple. It is just as a little illustration of the possibilities of random matrix theory. Thank you very much.
Thank you very much, Vincent.